A new model that solves the last remaining major questions about the birth of the Moon has been developed by astronomers. The findings reported in the journal Nature Geoscience explain why volatile elements found on Earth are missing from rock samples collected by the Apollo astronauts from the Moon. According to the hypothesis known as the giant impact theory, the Moon formed about 4.5 billion years ago when a planet which astronomers have named Theia collided with the early proto-Earth. The impact turned all of Theia and much of the proto-Earth into a magma ocean. Debris from this titanic collision was flung far into space where it formed a 19,900 km radius ejecta ring-like disk of molten and vaporized rocks and rubble around the Earth. The Moon was formed from this debris disk material over the following years as it coalesced and solidified. Up until now, scientists were unsure as to why the Moon is depleted in certain key volatile elements. Similarities in the geology of the Earth and the Moon have supported the idea that they share a common origin, the collision of a Mars-sized body into the ancient proto-Earth. However, lunar rocks lack key volatile elements found on Earth such as potassium, sodium and zinc. These elements couldn't have escaped Earth's gravity during the impact and so should have been found in the Moon-forming debris disk, the study's lead author Dr. Robin Canup said. That raises the question of why don't we find them in lunar rock samples? To understand what was going on, Dr. Canup and colleagues decided to combine new and existing models of how the Moon formed. They found that the core of the Moon initially coalesced from material in the outer part of the disk of debris left over from the collision. This part was sufficiently cool for volatile elements to condense. However, the outer lunar layers came from melt material from the inner part of the debris disk, and according to this new model, it was still too hot for volatile elements such as potassium, sodium and zinc to condense from vapor to solid. This explains why the outer part of the Moon, which had accreted from the inner debris disk material, has relatively low abundances of these volatile elements. Dr. Canup and colleagues also show that, although the inner disk eventually cooled to temperatures at which volatile elements can condense, this occurred after the Moon had moved away from the debris disk and its formation has ceased. The authors say that the volatile-rich inner debris disk material would have instead fallen down onto the early Earth. And once the disk cools enough for elements like potassium, sodium and zinc to condense into solids, the Moon's orbit has already expanded away from the disk enough to no longer be able to accumulate or sweep up this material, Dr. Canup said. So the basic picture is the Moon loses its volatiles, not because the volatiles escape from the system, but because the volatiles launched into orbit around the Earth by this giant impact, end up getting preferentially swept up by the Earth rather than by the Moon.